Thank you, Joe. The topic is air-sea interaction from the perspective of, call them intermediate scales, smaller than has historically been the climate focus, and larger than has historically been the boundary layer and micrometeorology focus. And over the last 10 or so years, it has become very clear that there is quite strong mutual relationship, correlation is one way to express it, and sort of sequential dynamical mutual influences on the evolution between certainly the lower atmosphere and the upper ocean, and occasionally with deeper penetrations. This is eye candy. It is an instantaneous snapshot of a nested regional simulation of quite high resolution by traditional ocean modeling standards of the surface vertical component of vorticity, here normalized by the Coriolis frequency. And so in the dynamical language, this is a Rossby number. It is not small, and therefore this is not geostrophic dynamics. And that essentially is the fundamental distinction between mesoscale and submesoscale. I'm going to talk mostly about mesoscale because that's where most of the air-sea interaction work has been done, but we have enough view of the submesoscale coupling to know that it extends down into that range as well. What you see in this picture is sort of a central ribbon that is the Gulf Stream that has vorticity of one side and the other on both sides of the central jet. The jet meanders, it occasionally fragments. Some very strong mesoscale eddies like a cyclonic ring or an anticyclonic ring are formed, but the main point of this picture, and I'll try not to show this in anybody's eye, I see it goes back, is you see all the fine structure. And the fine structure is the submesoscale. And it is everywhere in this image. It is different in different locations, and so it is statistically heterogeneous. But in particular, from the point of view of air-sea interaction, it is presenting a non-uniform surface to the atmosphere above on scales that are essentially bigger than certainly the oceanic boundary layer and comparable to the depth of the atmospheric boundary layer, that is on the order of a kilometer. Accompanying this surface vorticity variance, gradients, surface vorticity, velocity gradients, there are associated surface temperature gradients, most strikingly in the form of fronts and filaments, which are sort of ribbons of dense cold water near the surface. So in that sense, a filament is like a two-sided front, and both are prevalent. This kind of computational technology of being able to do nested grids down from larger scale solutions where the larger scale influence is carried down to the small scale, but yet the spontaneous emergence of small scale behaviors is allowed, has really been a very powerful technique, in particular in discovering the phenomenology that is called ocean submesoscale. And part of my visit here is to have conversations with the S-MODE group, which essentially is a NASA-sponsored submesoscale suborbital experiment that is going to go on in the next few years. Let me start with a sort of general background from a couple of perspectives. One is to say some lamentable things about climate science. It's the other dismal science. The famous dismal science is economics, and it's dismal because it involves people's poverty and suffering. Climate science is dismal because it's so hard. A few of the reasons are listed here. On the timescales of climate, we've seen very little. We have incomplete longer proxy records, but they're very difficult to interpret. And even in the measurement era, we are only measuring a few pieces of the climate system in a routine way. It's also dismal because you can't really say what the limits of climate are. If you're James Lovelock, then you talk about Gaia, and in fact it's the rabbits and the daisies that have created the climate in which we live. That's of course a fairy tale, but still, where is the limit of climate science? And what bothers me most as a theoretician is that essentially, apart from some rather simple energy balance type arguments, we really don't have a fundamental theory of the broadband variability that is climate. We don't even have very clear concepts as to how the pieces fit together. So in that sense, it's a very experimental science. It's a reasonably successful modeling science with things like general circulation models and Earth system models that are sort of like nature, but not with quantitative precision. And it's not at all clear that those models can ever be made precisely like nature. It's not even quite clear what that means. Heraclides said you can't step in the same river twice. It isn't at all clear how much climate repeats itself. But mostly it's because when you put together such complicated modeling constructs, you have to make so many decisions of judgment as to how you make the construction. Different groups make different decisions and they get different answers. Nobody thinks that the ice ages didn't happen. Nobody thinks that global warming isn't coming, but the numbers just don't agree in a detailed way. What is the strength is that the patterns and the relationships, the phenomena seem essentially right, and therefore the modeling is a very powerful approach. But what I want to emphasize here is that to me the bright part of the dismal science of climate is that we can tackle its processes one by one and try to work through them with precisions in measurement, precisions in modeling, and try to sort out the relationships. And what I'm going to be talking about today is essentially work in that spirit. Whether in the end we'll ever be able to assemble all the pieces in a way that seems precise is beyond this talk. So to sort of start with the longer view of air-sea interaction, it's of course something that people have worked on in various ways for generations. Some things are sort of very well understood, at least in a broad way. If you talk about the system effects, how do oceans matter to climate? Well, quite possibly it is the place where life originated. As I understood from my most recent Google survey, hydrothermal vents look like quite possibly the origins. It is, from a chemical composition perspective, a very important set of reservoirs for some of the most basic elements: carbon, oxygen, nitrogen, water. It's at least a reservoir, if not a regulator. There are questions about the last ice age as to whether the carbon storage in the ocean was the sort of the cause or the effect. It's probably some combination of both, but a big part of the signal. It's part of why we have a livable climate with not excessive gradients between tropical heating and polar cooling. Atmospheric poleward transport is the bigger part, but the ocean part is substantial as well. And it's also very clear from a weather perspective that there are a lot of storms that are much more intense because of the essentially thermal energy they receive in moving over the ocean. Certainly tropical cyclones are the dramatic example of this, but a lot of extratropical cyclones as well. Climate prediction, is it even possible? Out of my memory banks, I pulled the name of Jerome Namias, who is of a generation before me, and who really tried to develop a story of how seasonal and interannual predictability was possible. If only you knew the sea surface temperature patterns over the Pacific, you could say what the weather regime over the US would be. I think that this is a predictability skill that has not come very far since he began to work with it. We now understand this as preferred spatial patterns of relationships between variables, often called teleconnection patterns in the atmospheric context. They're certainly real. It's not at all clear they are model predictable beyond the empirical correlation lag time relations that exist. And of course, the causal basis of these patterns and their low frequency variability is still a rather murky story. And then micrometeorology, which I mentioned before, and in this context I would emphasize that it has essentially been a boundary layer science, and most of boundary layer science in both the ocean and the atmosphere is sort of predicated on local spatial homogeneity, temporal stationarity, in such a way that you kind of imagine a uniform environment for the boundary layer turbulence. And of course the mesoscale, submesoscale in the ocean and their correlated atmospheric patterns definitely stretch that conceptual framework. So let me turn to the mesoscale, submesoscale air-sea interaction subjects. I'm going to do so in essentially three pieces. The piece that is sort of longest developed is what I'm calling thermal feedback, which is essentially the response of the atmosphere to sea surface temperature gradients. The starting slide is simply the correlation with a spatial high-pass filtering to try to pull out sub-basin scale signals of the correlation between surface wind speed and sea surface temperature anomalies. And this particular product comes from a combination of scatterometry and altimetry. And so it's very clear that if you care about the wind, then the temperature underneath matters. And it's very hard to see in a causal way why the atmospheric variability, with its general progressive movement across any given sector of the ocean, would establish more slowly evolving mesoscale surface temperature gradients, which is what you're substantially seeing here. And so this is an indication essentially of mainly ocean effect on the atmosphere in this spatial high-pass filtering framework. Now the mechanisms are essentially two, and they're really just one idea. This particular cartoon at the bottom comes from one of Chelton's papers. The conception in the top line is one that essentially has been known by boundary layer meteorologists for a long time, which is that imagine you have a given wind in the troposphere above the boundary layer. If you're above a warm surface, then that velocity profile is going to reach deep down to near the surface. There's going to be a very strong shear layer near the surface if you imagine that it has to match the slowly moving current speed here. And therefore it's going to be a high stress situation. And so a warm ocean with essentially heat flux into the atmosphere is essentially going to be one of high surface stress. And the reverse, if you have a more stable boundary layer, you'll have a more gradual gradient, typically a smaller boundary layer as well, and a weaker relative stress, all for the same interior wind. And what that means, if you then think about a temperature gradient, and so just imagine this as a surface temperature front across which wind is blowing obliquely, then simply working out these different structural implications on either side of this gradient and the direction of the wind means that when the wind is more or less along a temperature front, you're going to get a strong vorticity generation, that is curl of the stress. When it's across the front, you're going to get a strong divergence. From the point of view of the ocean, wind curl is one of the primary drivers of the upper ocean boundary layer current system. It's often called Ekman pumping, and so this is going to have a strong action within the ocean in particular. But surface divergence is then the source of vertical velocity coming from the surface in the atmosphere, and so this is going to have a strong implication for, in both cases, talking about secondary circulations in the near surface flow. Here, from also a paper by Chelton, is simply computing climatological correlations with some, temporal filtering, so the more persistent patterns between divergence and downwind temperature gradient and curl and crosswind in the California current system, which is a region of very strong surface temperature gradients full of both mesoscale eddies and fronts and filaments, some of the filaments protruding from the coast out into the interior, all based on the fact that you have very cold temperatures near the coast that come from climatological upwelling and warmer temperatures in the middle of the gyre. And these are both highly correlated. If you compute regression coefficients, here done for the curl and here done for the divergence, they line up very well in a essentially linear relationship within the estimation errors from the observations of both. And so there is a very strong relation between wind gradient and surface temperature gradient. Not so much between mean wind or large-scale wind, which is still largely set by the sort of synoptic scale and larger atmospheric circulations, but rather what the meteorologists would call their own mesoscale. Here is one of the more striking examples of the thermal feedback that is from a paper by Minobi. It starts with 3 different atmospheric fields here. The surface wind convergence over what any oceanographer would recognize as the path of the Gulf Stream. These black lines are surface temperature gradients, and so this line of high temperature gradient is the Gulf Stream path. And so you have a very strong wind convergence, and in fact, these are time averaged, and in fact, when you look at the vertical velocity above the location of the Gulf Stream in a cross stream section, you see essentially penetrates all the way through the troposphere. And in terms of rainfall, this is a very high rain rate region, and it's locked in place by this ocean temperature structure that is the Gulf Stream carrying warm water from the subtropics over to the subpolar margin. Last example, this one more a snapshot of a place that is near the tropics, here's along the equator. This is the eastern tropical Pacific, and this pattern of black line temperature cusps is what are called tropical instability waves, originally detected by satellite radiometry. And in a comparison with the quickscat wind and taking the derivatives, here's a case where the divergence patterns clearly have a relation to the surface temperature gradients, as does, although to a somewhat lesser degree, the vorticity patterns, the curl patterns. And so in 3 very different geographical regimes, it's very clear that there are these strong coupled relationships because of the gradients of the stress, have a strong relationship to the vertical velocities in both the ocean and the atmosphere on each side of the interface. And this is where that point is made more explicitly, that when they're through the thermal feedback, that is essentially the effect of the ocean temperature on the stability of the atmosphere, the density stratification in the atmosphere, that you can have both wind divergence or stress divergence, and this has the sort of clearest implication for the atmospheric boundary layer secondary circulation, and through the curl, the Ekman pumping through the convergence of the stress-driven Ekman currents in the surface boundary layer. And the question of when they reach beyond the boundary layer in each medium is an interesting question, and one that is not nearly as well settled by observations, although that Gulf Stream example was a whole tropospheric atmospheric response. And these secondary circulations are strongly associated with frontogenesis. This is historically a principal concern of atmospheric people. There was the so-called Norwegian school that even decided that weather is really just a question of what the fronts do. That's not particularly a current view, but certainly fronts are a big part of the weather story. But fronts, as you saw indicated in that first Gulf Stream simulation plot that I showed, with its associated temperature fronts associated with the submesoscale vorticity patterns, is also very prevalent. And at any given time, if there are 5, 10 fronts in the northern hemisphere in January, in the atmosphere there are 500, if not 5,000 surface temperature, fronts in the ocean at the same time. And of course the frontogenesis is strongly associated in the atmosphere with cloud and precipitation patterns. These relationships evolve more slowly than the usual atmospheric synoptic evolution because of the more slowly evolving patterns of the heterogeneous structure of the ocean surface. Second topic, and this one is a newer topic, and one has been led more by the modeling studies, the process studies, whereas the previous one had been led historically more by the observations. And that is that there's a current feedback that if you use a bulk formula to calculate the surface momentum flux, the stress, with a drag coefficient and a density, it is the relative velocity, averaging over small scale things like wave and turbulence, that sets the strength of that stress. There's even a degree of further dependency in the drag coefficient on the sea state and the wind speed, etc., and the stability, but that's a secondary effect. And historically, this is usually approximated as just taking into account the wind component to this, and the argument is the very simple one that winds are stronger than currents, and therefore at some level of approximation it must be true. However, at a sort of next level of correction, this atmospheric stress is corrected by an ocean stress, which, when the ocean currents are weaker than the wind, is essentially predicted to be by this formula a linear relationship with the ocean current speed, and furthermore with a proportionality constant in this regression coefficient that itself is proportional to the wind speed, and with a minus sign that is essentially inherited from that minus sign. The most dramatic effect that comes from this kind of coupling feedback is that if you compute the eddy wind work done on the ocean, then with that approximation, this is a negative quantity no matter which way the currents are flowing, and therefore this is a kinetic energy transfer from the ocean to the atmosphere. The atmosphere, of course, is being dragged by the surface, and this is a way of saying that it's being dragged a little less than you might think that if that's the only part you looked at. From the ocean perspective, the effect is very dramatic in the sense that this is what has been called an eddy killer. The currents we're talking about are primarily ocean eddy currents The atmospheric wind speed is a combination of large-scale atmospheric structure and mesoscale structure. But this is a very strong kinetic energy sink for ocean eddies. And let me actually make a remark here, and then I'll come back to where I was. This is a plot of the mean path of the Gulf Stream in terms of current speed, something in excess of a meter per second in places. It's a very stable path. And if you go into the science of climate modeling, historically, climate models were very coarse resolution. They didn't do anything to resolve ocean eddies. And in ocean models, the Gulf Stream would never separate at the right place, even though observations show that it's quite locked in this location. As people began to resolve eddies, doing what is the current sort of frontier of IPCC class modeling, at least outside of Germany, people began to have resolutions about 10 kilometers, and they began to see the Gulf Stream separate in more or less the right place for what is essentially a region of inertia. If the currents are strong enough and the boundary turns a corner, then the currents will tend to keep going. And so in that sense, that climate bias began to be corrected. But the other problem is that once the resolution began to be better, you had too many eddies. You had too strong eddies, and you began to have too meandering a Gulf Stream. And in fact, this current feedback is a remedy to both, which I'll return to in a moment. But let me first come here. This is a cartoon illustrating the feedback over an ocean eddy depicted by this circular flow. And you imagine there is a background wind, on the two sides, here's what the ocean kinetic energy wind work looks like if you have a symmetric current and a wind that is unaltered by the eddy flow, that you essentially have equal and opposite stress on each side, and so the net effect is zero and no energy exchange. However, with the feedback that I've been talking about, you will have a much stronger stress where the current is opposing the wind and a much weaker stress where it isn't. And this will lead to that negative wind work due to the differential stress across the sides of the eddy. And of course, not in this cartoon is then the back effect on the atmosphere. That is, it's got a stronger stress in one location, a weaker stress in another. That will drive an atmospheric secondary circulation. But the amount of energy exchange we're talking about here in this quantity, which of course is equal and opposite to the energy exchange with the atmosphere, is a small fraction of the atmospheric energy. And so from an energetic perspective, this is not necessarily so consequent on the atmosphere, but it is a return of energy to the atmosphere. But it's very important for the ocean. Here are comparable regression coefficients of this proportionality constant to the stress correction versus wind speed. This is a California current study, and being a modeling process study, essentially three cases can be contrasted. One in which you take a data set of a specified wind field and you calculate your evolution of the ocean model, and you come back with essentially no correlation between the wind speed change and the stress change. If you keep the same atmospheric wind from that data set provided by reanalysis or something like that, and now run an ocean but with this stress bulk formula relation that depends on the relative velocity, you get a very strong negative regression coefficient. And if you now fully couple using that coupled stress relationship, you ameliorate this some extent, but it still remains primarily this eddy killing interaction between the structure of the wind and the structure of the ocean currents. Here's a global estimate of this regression coefficient between the stress and the ocean currents. It comes from combining altimetry and QuickScat, and it's almost universally negative. And furthermore, if you plot it as a regression against sort of the mean wind speed of the regions, then you see that in fact it is this anticipated roughly linear relation, and it's in the high latitudes where the winds are stronger that this regression relationship is stronger. And so here is I think this is the next slide. No. Here is from the same study a estimate of this eddy windward kinetic energy exchange. I think the color bar is chosen in a way to highlight the regions of the strong exchange, but the strong exchange is essentially all negative, and these are regions of strong currents, mostly associated with western boundary currents or the Southern Ocean. But these are essentially empirical demonstrations on a global scale of the importance of this current feedback. Here's a more recent study with carrying the simulation down to even finer scales. And this is a depiction of the instantaneous ocean vorticity at the surface. I hope it reminds you somewhat of the patterns, similar but different, that we saw in that original plot over the Gulf Stream regional simulation. That is, here's essentially a strong mesoscale eddy structure, and these fine structures are the submesoscale. If you high pass filter the eddy windwork in this region, except right at the coast, you again get this energy exchange from the ocean to the atmosphere, this eddy killing thing, but now to a whole new population of ocean eddies, the submesoscale fronts and vortices, rather than the larger mesoscale eddies. This picture I've showed, and essentially the stabilizing role of the current feedback is illustrated here. First, let's talk about the path. These lines are bounding sea surface height contours. There's a sea surface height jump across the Gulf Stream associated with the geostrophic jet flowing across that jump or along that jump. And the red is the AVISO climatology lines of the Gulf Stream path, and the blue is an uncoupled simulation where, because it's a high resolution simulation and the Gulf Stream is strong and there's plenty of inertia for separation, the separation position is fine, but there's far too much meandering of the path that is in fact stabilized by this current feedback. You can see a similar thing if you look at the surface eddy kinetic energy. Here's the observed, here is the uncoupled, and here's the coupled. This is larger and more wandering and spatially distributed in its pattern. So not only is this sort of eddy killing role there, but there is this sort of control of the path of the major currents, and as we saw from the earlier thermal feedback, the path of the Gulf Stream with its warm temperatures is a very strong control on North Atlantic weather patterns, North Atlantic climate. Third topic, these are all results from regional atmospheric models and regional ocean models in which the boundary layer turbulent fluxes are parameterized. They're talking about circulations on the scales of kilometers horizontally or larger, and boundary layer turbulent eddies can be on scales of meters or smaller. And so the long practice in climate modeling and numerical weather prediction and most ocean circulation modeling, certainly of the global scale, is that you have to parameterize the boundary layer turbulence. And as I've been hinting at in the presentation so far, the boundary layer interaction is at the heart of this air-sea mesoscale coupling. So the question is, and this is a sort of next step in it, is what happens if you start doing a more complete calculation of the atmospheric boundary layer. And in particular, this is a large eddy steady flow of the thermal feedback. That is, the only ocean heterogeneity here is a surface temperature front across which the wind flows in the example I'm talking about. And the conception here is you have a prevailing, in this case wind, a prevailing current. And as a result of this air-sea coupling, you're going to develop overturning circulations, essentially in the plane perpendicular to that primary flow. And so here's the primary flow. It is a fixed geostrophic inflow at the top of the boundary layer. This is the surface. In this case, it's essentially a surface with no currents, and so it's a stress entirely determined in terms of the atmospheric wind speed near the surface with Money-Nabokov kinds of representations. And there is a surface front here of a couple, this is I think approximately a 1 kilometer wide front. In this case, with a delta T positive, it's going from a cooler surface that is weakly convective to a somewhat warmer surface by a couple of degrees, which is somewhat more convective. The boundary layer top, certainly in the upstream direction, is about this high, above 500 meters. And what you're seeing in these two contrasting plots is the vertical velocity averaged over the turbulence and averaged along the front in the third direction that results as a function of this. If there were no front, there would be no mean vertical velocity. There would just be turbulent vertical motions. And what you see when you transition into the more convective boundary layer is that you have a very strong downward velocity in the entrainment layer that essentially is descending from closer to the front to, more to the interior of the boundary layer over a distance of about 10 kilometers. That is, the principal effect that you're seeing is not co-located with the surface temperature front, and so this is something that you wouldn't pick out from local correlations. You would have to somehow have a sense of spatial structure relations. And if this, in a sense, is viewed as heating, then it's somewhat counterintuitive from at least sort of homogeneous thinking that you would then have more descending air. And in fact, you see the reverse when you are going from a somewhat warmer to a somewhat cooler across the front, where you have essentially a structure that over a somewhat longer distance develops from the surface and is a rising velocity. These are components of the secondary circulation I've been talking about. If we just look at a couple of more measures of this flow, this is one of turbulent intensity measured by the vertical velocity variance associated with vertical transports, momentum and buoyancy. And you see these very different patterns of weaker variance on the cooler side, more variance on the warmer side, same thing down here. But in addition to this transition to two more homogeneous regions far upstream and downstream, you have a very much a localized response of the turbulence being particularly strong. And in this warm front case, it's clearly reaching into the entrainment layer, the inversion layer. And if you now start to think of clouds, which are missing in this particular simulation, this is going to be impactful of those low cloud stratocumulus that occur at this level. If you look at the mean overturning stream function, that is something that it's a stream function for flow that is 2D non-divergent in this plane because things are uniform along the front, that it is related to the horizontal velocity and vertical velocity in a way that the flow is along these isolines. And now you see the sense in which the downward flow descends from the entrainment layer in this warm front transition case, that it is essentially a flow from far upstream that closes locally. And so the gradient action in the atmospheric boundary layers in this region, same thing in the transition to the cold front, except that the vertical structure is somewhat different, the response is somewhat delayed. And here it is principally a local updraft that is forced over the colder water and a primarily downdraft that is forced over the warmer water. And the last, I think, slide in this is this one, where if you look at the turbulent heating profile in these two cases, that is the convergence of turbulent vertical flux normalized by the surface flux in the upstream direction, you see a very strong heating just close to the transition across the warm front. But that heating then penetrates up into the entrainment layer. It's particularly strong cooling in this downstream location, and as we've seen, the mean vertical velocity is then essentially along this path. Here you see a strong local cooling as you transition over the cold front, and you see a very strong contrast in a very short distance between the strong vertical heating over the warmer water and the much weaker vertical transport heating here. And this effect on the boundary layer flow is very much more localized. This is a new calculation. It's a big calculation. It's the start of a family of calculations that would need to be done, looking both at thermal feedback and current feedback, looking at sensitivity to wind direction. It actually matters a lot that these are all examples of the wind across the front. And there are analogous studies that partly have been carried out and can be carried further in terms of the oceanic boundary layer to try to sort out these secondary circulations. So, to summarize, these two mechanisms, both of which at a sort of very local level we understand very well. We know why surface temperature gradients matter to the atmospheric boundary layer. We know why ocean currents matter to the surface stress, which affects both boundary layers. That they're widespread and significant in the lower atmosphere and upper ocean. If you're looking for more than just, call it surface flux structure, it's the secondary circulations engendered in each of these ocean and atmosphere layers adjacent to the surface that have the greatest potential for larger scale, more remote, more climatic consequences. I've mentioned frontogenesis previously, which certainly happens by the secondary circulations there, here due to the air sea flux heterogeneity, but also for the entrainment. And in the atmospheric low cloud layer, this is where the entrainment effects may be most evident. And if you have a heterogeneous surface, then you would expect a heterogeneous cloud layer in some sense. And I don't think I know this is not the prevailing atmospheric paradigm for cloud organization, but it is certainly potentially consequent for that. In the ocean, the entrainment flux is a strong regulator across the pycnocline and the nutricline at the base of ocean vertical heat transport, essentially from the interior into the surface boundary layer where it's available for air-sea exchange. By the regression relations that I've shown you, there is certainly an available parameterization for ocean circulation models about how to represent the current feedback if you don't have a coupled model. There's a paper now out essentially on the question of if you have an atmospheric wind product or an atmospheric stress product, how should you force an ocean model, recognizing that this effect is present. You don't need, of course, a parameterization if you have a fully coupled model, because then you have both the wind and the current ingredients for calculating the stress. We've thought less about whether you want to start juicing up your parameterizations in climate models for the thermal feedback. It is something that if they have the resolution to see the ocean surface temperature gradients, they ought to be able to take care of by themselves. So we're essentially in an era of process studies that this sort of influence has not really percolated into the climate modeling practices, and certainly the coarse resolution of global models used for most climate studies is an inhibition to bringing these ideas in, but nevertheless they are important. And we're talking about air-sea flux gradients and secondary circulations over periods of multiple days, or at least multiple hours, which are the sort of characteristic evolution times for ocean surface heterogeneity in temperature and currents, and on the rather smaller scales that are essentially encompassing the mesoscales and the submesoscales. And as a last remark, I don't know if anyone here is involved, but we are on the verge of, by our field standards, an enormous experiment about to occur in the northwestern tropical Atlantic called Eureka in Europe, which is making the bigger investment, and called Atomic in this country, which is a NOAA program. Its stated purpose is to try to understand climate feedbacks in low trade tropical cumulus and understand their sensitivities to climate change, but a very central aspect of that is trying to understand cloud organization patterns, which are almost certainly important parts of those climate sensitivities. The experiment was essentially conceived by atmospheric people, Bjorn Stevens at the Max Planck Institute and Sandrine Bonny in Paris. And of course they didn't even think about the ocean, because everybody knows that cloud organization is something the atmosphere does by itself. But they made the mistake of talking about it, and so there is now an ocean component of it. I think it's up to about 4 ships. The latest one that went around is apparently the Barbados government is willing to rent a pleasure yacht that can be enrolled in oceanographic survey measurements, although I'm not quite sure how that works. Starting in January, essentially a month-long experiment, and in addition to the sort of lower atmosphere cloud dynamics considerations, trying to close the mass balance, trying to understand mesoscale vertical motions in the atmosphere, essentially by solving the continuity equation, by making airplane patterns that calculate the horizontal wind well enough in a circuit that you can calculate the divergence. This is a technique that they've shown in some preliminary experiments will work. Will also be able to look at the question of what these eddy, thermal, and current feedbacks might do to the measured atmospheric circulation patterns and thus the convective cloud patterns. Or maybe they won't do anything. I mean, this really is kind of a new question experimentally, but it is going to be quite a big experiment. And I'll quit there.
Jim, it's a great talk. Thank you. And you talk about the contribution of the thermal and the current coupling to the atmosphere and ocean over all different scales. So can you
over scales in which there are strong gradients in the ocean surface, which means not too large scale. I mean, the really large scales have weak gradients.
Yeah, you talk about mesoscale and the submesoscale. Can you comment on the relative contribution of the sub versus meso? And I think the answer probably depends on the spatial temporal scales. But
I'm sure it does. At this point, the science of process experiments and data analysis is moderately far along for the mesoscale coupling, where in particular the satellite measurements of altimetry and scatterometry and radiometry sample those scales reasonably well. Dudley Chelton and his colleagues in particular have exploited those data sets very well to examine that, although with less attention to the current feedback. Most of the modeling studies have been done with good mesoscale resolution, but still not adequate submesoscale. There's one paper that I touched on that shows that at least the current feedback is still strong, even on smaller scales, but that's mostly unknown territory, for which we need new satellite missions, of course. Low altitude satellites with very high spatial resolution.
Other question?
So Jim, as you know, in ESMO we'll have an optical sensor supposed to look at the ocean color. It doesn't work when there's fog, but it could do something if there's a correlation between the fog clearing and the ocean submesoscale. Do you think there's anything?
As I understand fog, it's very much related to the contrast between air temperature and the ocean temperature. Now, the trouble with California fog, particularly when you get to Central California, is when it's there, it's really solid. And so what you're talking about would potentially be most informative if you were kind of in the marginal transition regions between patchy fog and, part clear. But yes, I think that's a potential, and certainly atmospheric stability matters, and I would guess vertical velocity and secondary circulation matter to fog too, although I've never heard that story before. And of course, ocean color is strongly indicative of ocean currents and sea surface temperatures because they're all there for the same surface convergence and secondary circulation regions.
Jim, just one question. You mentioned that there is a transfer of lower kinetic energy between the ocean and the atmosphere because of the mesoscale. We know that mesoscale explains a lot of the kinetic energy in the ocean. It means that there is a huge transfer of kinetic energy from the ocean up to the atmosphere. Do we know what is the impact of this transfer of kinetic energy on the atmosphere, on the jet stream?
I don't. I think that hasn't been followed. As I remarked, in general, the atmosphere has so much more kinetic energy that this effect may be relatively less important, for example, on the tropospheric scale than it is to the ocean. But if I try to make the climate justification related to this, we know ocean eddies play a great deal of climate balance in ocean circulations, particularly in strong current regions. And the problem with uncoupled oceans without this kind of current feedback is the eddies are too strong. We used to not have enough resolution, and so our problem was to make them stronger. Now, once you go beyond this eddy permitting category of present IPCC models, you start to have eddies that are too strong, and this is one thing that will certainly work against that and seems, in the examples I've shown, to bring the ocean energy level closer to what is observed. Just how, call it surface stress heterogeneity, which is really the way the atmosphere will see this, which is in a certain sense imposed heterogeneity because it's, if the wind is initially thought of as sort of smooth on larger scales, but for its boundary layer turbulence, and now you have heterogeneous currents, and so you have heterogeneous stress. What kinds of atmospheric responses does this create? And I think the potential for atmospheric circulation, secondary circulations being important is greater than the potential for the extra energy supply that it will get from the eddy windwork. But that's also unexplored territory. The thermal feedback, as in that Gulf Stream troposphere picture at this point, is clear, at least in some cases. The stress feedback effect on the atmosphere is less clear, to me.
More questions? One.
Yeah, so I had a question about, you showed the Gulf Stream simulations, and with the current feedback, you had more realistic structure. So I guess I was wondering if, thinking from an ocean modeler's perspective, if you just want to have a realistic structure of the current, how far can you get by just, if say you have winds from an atmospheric model, if you just take the current into effect in the bulk flux without worrying about the feedback per se, but just including that, the differential?
The thing I call the parameterization, which is this stress anomaly equal to a regression coefficient times the ocean current, gets most of the effect. So I think the potential for making ocean models better without coupling is pretty high, certainly compared to not having the feedback. But of course the future is coupled models.
Graham, one last question.
Yeah, it was great talk and very thought-provoking. I think kind of opening up kind of new area of thought for coupling between the ocean and the atmosphere through the secondary circulation, ultimately clouds and weather and so on. All I have is some anecdotal example. I was at a Royal Met Society meeting about 3 years ago, and one of the big topics of discussion were the regional forecasts. The regional forecast that Met Office were providing, where they run it with a coupled ocean of 1 kilometre resolution. They found that the 1 kilometre resolution ocean had a significant impact on weather in the UK in their forecasts. It's just anecdotal.
I like the anecdote. Is it a paper?
I haven't followed up with them for a couple of years, but it's no doubt in the literature somewhere, and I can dig this
There is
around.
that, I can say,
There is a paper?
Sarah,
So
But that opens up both the thermal and the
Yeah.
current
They
feedbacks.
came away, their message was, they believed to advance weather prediction on certain scales, whatever it was, regional in the UK, that you needed to have ocean modelling coupled at that kind of kilometre scale. That was their kind of conclusion. Right? So it's anecdotal, but it's kind of interesting.
It is. As part of the Eureka program, Bjorn Stevens is trying to roll out a coupled model at 2.5 kilometers. Good luck to him. But
Probably
Yeah.
regional though, right? Regional.
no, he's trying to do it globally.
Private global.
More power to him. But look, this has to matter in ways that we, in a climate context, barely understand, because the curse of climate is that everything is probably connected to everything, and you don't know till you look.
That's a wonderful way to. Before we thank Jim again, you have some time after, so if you want to come and speak with Jim individually now, that would be a good time to do it. Otherwise, thank you again for a wonderful presentation.
Thank you.